Okay, so I will start. Okay. So today we are going to present tutorial 7A for WOA 7001 advanced algorithm. So my name is Song Yann. Okay, so together with me, will be Mohamed, Moussad, Mohamed Ibrahim. Then you have Kou Weijia and Zhiyu. So this particular video is broken into 4 parts. Okay, so binary search tree, AVL tree, 233, and red and black tree. So I will be presenting the first one, binary search tree. So binary search tree, is a node-based binary tree data structure with the following properties. Number 1, the left subtree, of a node, contain only nodes with key lesser than the node key. The right subtree of a node contain only node with key greater than the node's key. The left and right subtree each must also be a binary search tree. And number 4 is, there must be no duplicate nodes. For example, so 100, so the left 20 will be lesser than 100, 500 will be greater than 100. That's why 500 is placed on the right-hand side. So this is one binary search tree. So the subtree, for example, 20, same goes here. 10 is lesser than 20, so 10 is placed on the left hand. Then 30 is greater than 20, so that's why 30 is placed on the right. So this is also a binary tree search tree. So in altogether, it will be a correct binary search tree. So insertion, so we start from the root, we compare, the inserting element with the root. If it's less than the root, then recurse for left, else recurse for the right. So let's say we want to insert 40. So we are going to compare with 100. Since 40 is less than 100, so we are going to look at the left hand. So we are going to ignore the right tree. After searching to the end, just insert the node on the at the left, if less than the recurrent, else is the right. So then we are going to compare 40 with 20. So 40 with 20. So because 40 is greater than 20, so we are going to go to the right-hand side. Then we are going to compare 40 with 30. So because 30 is 40 is greater than 30, so that's why we are going to put the node 40 here. So this is the final outcome. For delete of the binary search tree, there are 3 conditions. So the first one is the node that to be deleted is the least, means to say the last one. So what we're going to do is we just simply remove it from the tree. Let's say, so we want to delete 20 from this tree. So since 20 is the least, so we just discard it, no problem. Then node to be deleted has only 1 child. Then we have to copy the child to the node and delete the child. So for example, if we want to delete 30, so this is the location of 30. So since 30 got 1 child, which is number 40, we need to copy 40, put it inside 30. Then after that, we are going to delete the 40. So the third one is not to be deleted, has 2 children. So we have to find the in-order successor of the node, copy the content of the in-order successor to the node, and delete the in-order successor. So for example, here we want to delete 50 from this tree. So 50 got 2 children, 40 and 70 respectively. So the next in-order successor will be 60. So we are going to copy 60 and place it to the node that we want to delete, which is the 50. Then after that, we are going to delete the 60 here. So this is what it means. So in order for you to get the maximum and minimum value from the binary search tree, what do we need to do is, for maximum, we can find the maximum value by traveling to the right pointer until we reach the rightmost of the node. Taking this particular example, so the maximum, okay, so 60, the right will be 70, 70, the right pointer point to 80, so 80 is the maximum. The minimum will be vice versa. In the binary search tree, we can find the minimum by traveling, okay, the left pointers until we reach the leftmost node. Binary search tree, okay, sorting. We need to sort the array before converting into a binary tree. So number one, okay, so let's say we have an example 6, 2, 7, 3, 4, 5, 1. So there's no repeat node, so it's good. So we are going to sort it out, okay, and become 1, 2, 3, 4, 5, 6, 7. Then after that, we are going to get the middle of the array. So 1, 2, 3, 4. 4 is the middle. Then after that, make it as the root. So this will be the root. Recursively do the same thing for the left half and the right half. So the left half will be 1, 2, 3. We are going to get the middle, which is number 2. Then after that, we are going to put in 1 and 3. Then for the right half, which is the 5, 6, 7, we are going to get number 6 and make it as the root. Then after that, put 5 on the left, put 7 on the right. So that is how we're gonna get it. So searching, we will start from the root, okay, then we will compare the value to be searched, okay, with the value of the root. If it's equal, then we were done with the search. If it's lesser, we are going to concentrate on the left subtree. All right. Then if it's greater than the root, okay, then we are going to go to the concentrate on the right subtree. So we are going to reduce, okay, like this until we find the elements or until our search space, okay, is reduced to only one node. Then we are going to return the value. The time complexity. The average time complexity of the operation, okay, of a binary search tree is BO of log n. Okay, so we have to consider the worst case. The worst case time complexity, it will be BO of n. It is because, okay, if we have one very unbalanced tree, for example, in this tree, so 50, 30, and 20, right? In order for us to search for 20, we need to travel from 50 to 30 to 20. Then it will be whereby n is the height of the binary search tree. So this is the n lah. Okay, so then if we want to insert 10, for example, so we need to travel from 50 to 30 to 20, then after that 10. Okay, so if we want to search for the minimum, okay, 20, we are going to do the same thing also. So in most cases, okay, we may have to travel from the root to the deepest leaf, okay, which is the left or the right node. The height of a skewed tree, okay, may become n, and the time complexity will be BO of n. Then I'll pass, okay, the presentation to my colleague. Yeah, okay, then you can continue.
Sorry. We will discuss regarding AVL tree algorithm. The structure of this algorithm, it is high balancing binary search tree, which rebalancing thresholds. Check the height of the left-right subtree and make sure the balance factor will be less than 1 or less than -1. In the diagram, we have 3 pictures in balancing. If we check each BF for each A, it is balancing 0, and B 1 - 1, it will be 0, and for C, it will be 0. But in the second diagram, if we check A, it will be 0, and B, it will check it will be 1, because it has left subtree and it doesn't have right subtree. It will be 1 minus 0, it will be equal 0, it will be equal 1, and for C it will be equal 2. So this tree, it will be unbalanced. And for the other diagram, it will be also unbalanced, because we have two right subtree and doesn't have left subtree for A node. But for B and C, it will be balanced, because there is only the factor, it will be 1. If balancing factor 1 or minus 1, so it will be a balanced node. And we have 4 rotations. The first one is left rotation. Left rotation in this diagram, for A, B, and C, BF equal 2 and BF equal 1. So we make left rotation. After we make left rotation, so the diagram will be like this: B in the middle, and A, it will be in the left subtree for B, and C, it will be right subtree for B. For the right rotation, the second rotation mechanism, we will make right rotation, so B, it will be also in the new root, and C will rotate to be in the right subtree for B node. Other left rotation, it will be double rotation, left right rotation and right left rotation. For left right rotation, we make for example, here we have BF. If we calculate the BF for B, it will be 0. For A, it will be 1, and for C, it will be 2. So the node here has been inserted into the right subtree for the left subtree for node C is unbalanced node. So if we have unbalanced node, so we'll make rotation. How can we make rotation? The first one, we will make left rotation for node A. So for B, it will be the left subtree for C, and A, it will be left subtree for B. After that, we make right rotation for node B. So the balance factor for all, it will be equal 0. For the last rotation type, it is a double rotation also, and the combination of right rotation followed by left rotation. The first one, we will make right rotation for long C, and after that we will make right rotation for node B, starting from node B, so the tree is balanced. For BF, it will be 0 for all nodes. The insertion tree for AVL tree